I hope you guys are having a good start to your day. Today, we are going to continue balancing chemical reactions and talking about balancing chemical reactions. Now, what I want to show you guys right from the start is kind of actually what we're going to do is I'm going to go ahead and kind of move on to the next part of what we're doing with respect to balancing chemical reactions. And, that might be a little bit of a review. Mole. We've talked about moles before, and we're going to do it again. Now, what you should expect here and what you should expect today is a little bit of a review on a mole or the mole. And then we'll get into kind of looking at some examples and some good practice problems to do. So, the first thing, before we proceed into doing like good practice problems for today or for this content, I'll give you a little bit of a refresher on the mole. So a
I
mole
know that easy. Fuck.
is just a okay. Um, if you're ever unmuted or anything like that, please be cautious of whatever you're saying because that gets picked up by the captioning. Um, So please, if you don't mind, remain muted. If you have something to say, you can add it to the chat. You can also unmute yourself, but if you've got something playing in your background or something like that, that will get picked up by the captioning and that will be displayed for everyone. I don't really want that. The video for last class, I mean, I thought that it was, but I guess it has not yet been, so I will get that posted a little bit later today. I'll also post today's. Um, so it's okay. 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 So a mole, it's a dozen. We've talked about moles before, and here what we're going to be doing is we're going to be applying some of the things that we did. You know, if you remember the last time that we talked about moles, um, we talked about relationships between mass, number of particles, and how those things relate to moles. Um, if you remember, one of the very important places that we had questions related to moles was we used the periodic table. And if you looked at the periodic table and you saw, I'm going to go ahead and draw over here on the left-hand side of the screen. If you looked at the periodic table and you looked at the atomic symbol for carbon, what you'd see that, or what you would see is that carbon has a couple of numbers on it. One of them is 6, and then one of them is approximately 12.01. I can't remember the exact number. I'm going to leave it at 12.01 because that's kind of the point. Um, and this number right here, that 12.01, that gives you it gives you the atomic mass. Oh, let me rewrite that. The atomic mass of one carbon atom. And atomic mass is going to be measured in atomic mass units or AMUs. So this would be one carbon atom has a mass of 12.01 AMU. Now, an atomic mass unit is a little bit, I don't know, I always thought that it's a little bit abstract because, it's not a mass unit like a pound or a kilogram or a gram or anything like that. Um, So what I always like to think about this 12.01 as being is rather than saying 12.01 AMU, I say 12.01 grams per 1 mole. You might also see that written as 12.01 grams per mole. So let me ask you, and go ahead and respond in the chat with this. What is the approximate mass of 1 mole of carbon atoms? 12.01. Perfect. So if I had 1 mole of carbon atoms, that would have a mass of 12.01 grams. What if I had, and go ahead and respond to the mass of, if I had 6.02 times 10 to the 23rd carbon atoms? What's the mass of that? Add it to the chat. Perfect, 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 perfect. Fantastic. And just between you guys, the 65 of us, I wasn't just pumping my hands like this because I'm excited you guys got that answer right, but also because tomorrow is opening day of the Major League Baseball season. I love baseball. Um, so I'm excited about that, but I'm also excited that you guys got 12.01. So if you have 6.02 times 10 to the 23rd carbon atoms, you have approximately 12.01 grams of carbon atoms. That's the mass of that many atoms that in grams there. Okay. So understanding those connections is one of the important parts about balancing chemical reaction. Now, some of these slides are the same as we previously saw. Yep, there we go. Mole Day was October 23rd, and that's whenever I know whenever I was in high school, my teacher had us, we had activities where we could celebrate Mole Day. And, you could make like draw a little mole or something like that. And I remember one of my friends he was not very nice to another person. Everyone was drawing their moles, and you can make it a character. And one guy in this class drew Mole Nito, and my friend was like, "What is Mole Nito?" And he said, it's like the mole version of Magneto from the X-Men." And my friend was like, "You're a nerd." At any rate, my friend was not very nice. And I wish that I could be saying that the kid who drew Mole Nito was my friend was my enemy. But anyway, Mole Day, October 23rd, 10 to the 23rd, hence 10 month and 23rd the date. Okay. So all of these things right here are moles, are an individual mole of different things. We've got helium. A mole of helium fills a balloon like that. A mole of iron, a mole of sulfur, a mole of mercury, and a mole of copper. They're all a little bit different from one another. Now, whenever it comes to balancing chemical reactions and moles, I'm going to go ahead and jump ahead quite a bit. I've got all this in here, but really what I want to work on is I want to go ahead and work through some practice problems. And so I've got a couple of blank slides here. And what I want to do is I want to go ahead and come up with a chemical reaction. Now, this is a chemical reaction that I've kind of arbitrarily come up with. We've got KCl plus, or yeah, let's see, NaOH. And then I put my arrow. Does anyone remember the word that we use to describe the arrow there? I'll give you a hint. It starts with a Y. Add it to the chat. It's also kind of a stop. Yields. Perfect, Emma. Awesome. So KCl, Georgia, great job. KCl plus sodium hydroxide or potassium chloride plus sodium hydroxide yields. Now we just sort of switch. And you don't have to, this is not something I'm expecting you guys to be able to predict the products here, but the products are going to be KOH plus NaCl. Okay. Now, whenever we're balancing a chemical reaction, what we want to do is we want to make sure that the number of atoms of each type is identical on each side of the reaction. So, what I always like to do is I like to kind of take an inventory of all of the different atoms that are in my reactants. Got K for potassium. I've got Cl for chlorine, Na, got oxygen, And last but not least, I've got hydrogen. Now, the first thing is I'm going to say, I always like to kind of keep it in a line. I'll account for the number of potassiums on my reactant side, and then potassiums on my product side. Done. Chlorines, chlorines. Sodium, sodium. Oxygen, oxygen. Hydrogen, hydrogen. Okay, now go ahead and tell me in the chat with a Y or an N, is this balanced? Is this chemical reaction balanced? It is. And that is going to be my segue to using our first poll question for the day, which is registering right here. Okay, I got a poll question up. I'm going to leave that up for a little while. When balancing a chemical reaction, you can change subscripts or coefficients. Now, this one was balanced, so we didn't really have to change anything. But if it were unbalanced, what would we do? Well, give you a little bit of the answer. Coefficients. Remember, coefficients are the numbers that come before or that precede our symbols for our different molecules. So if I wanted to, balance this chemical reaction, I would say, okay, well, I can change this, 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 this as I see fit. Now, another way, so we will get to a reaction that we have to balance in just a little bit, but what I need you to know is that the coefficients are what we can manipulate. The subscripts, we do not change those. Now, there's still time to answer that question, but what I want you guys to think about with respect to this is we established our lowest common ratio of reactants to one another and reactants to products. So, can anyone tell me in the chat? I'm going to go ahead and end the poll here. 77% of the class got coefficients correct. Great job. Back. What is the ratio of potassium chloride to sodium hydroxide? Add it to the chat. 1 to 1. Okay. So we've got a KCl. We could look at this and say KCl to NaOH. 1 to 1. Okay, we're good there. Now, would you agree at a Y or an N that when we have this balanced chemical reaction, we also have a ratio of reactants to products? And maybe it would be a little bit more direct where we've got 1 KCl to 1 KOH. Add it to the chat, Y or N. Y if you see that, and N if you don't see that. Because this is our balanced chemical reaction. Okay, great. We have a ratio. Whenever we have a perfectly balanced chemical reaction, we've got we have a ratio of reactants to one another and products to one another. Now, with that in mind, I want you to add to the chat how many KOH would I produce if I had 2 KCl and 2 NaOH? 2. Perfect. Great job, everyone. Okay. Now, I'm going to switch this a little bit. Let's say that I had 100 KCl and 2 NaOH. How many KOH are going to be produced? Wonderful. Oh, okay. Well, I'm happy that you answered 100. If we have 100 KCl and 2 NaOH, what do we need in order to react a NaOH with a KCl? We need 1 NaOH to react with 1 KCl. Okay, so I always like to kind of think about these as rounds. So in round number one KCl reacts with one NaOH. Okay, so after that, what's left over? Well, there's 99 KCl's and one NaOH. So then in round two, one KCl will react with one NaOH. Now what's left over? How many NaOH remain after round two? Add it to the chat. Zero. You're absolutely right. Okay, so we've got zero NaOH that remain. How many KOH did we produce? We produced two KOH. We've got 98 KCl left over. Okay, so with that in mind, if I told you that there were two important terms, limiting reagents and excess reagents or reactants. Reagent and reactant are kind of interchangeable terms. Which one of these two reactants, KCl or NaOH, would you identify as the limiting reagent? Which one has a limit to it? NaOH. Perfect. You're absolutely right, Dolce. Great job. KCl is in excess. One way to, articulate that is we still have KCl left over. We have excess KCl. And whenever you have a chemical reaction where you have two reactants, one is limiting and one is excess. So the one that is limiting is not the one that's in excess because it limits the amount that we can produce. Okay. So on a scale of 1 to 3, let's go with 1 being super simple, I got it, and 3 being, man, I don't know, this is a little tricky. Answer me the question, how difficult is a balanced chemical reaction where every coefficient is 1? Using this as a model, would you say it's 1, pretty easy, or 3, it's a little dicey, or 2, oh, well, I think excess reagent only applies to 1. No, Emily, I'm happy that excess reagent, okay, Emily, that's a fantastic question. Love that question. The reason that's a great question is because this right here, you should think about a balanced chemical reaction as kind of like the rule. And then this shows, I'll say balanced reaction. Georgia, that's a great question. And yes, you will. But we're going to get there, okay? We're going to be able to do that in just a little while. The balanced chemical reaction is the rule. This and the important thing about this rule is it has the lowest whole number ratio, or ratio, not ration, ratio. So I mentioned this the other day. You could think about a chemical reaction as being similar to a recipe. You need this many cups of this many cups of this. Now, whenever you're baking cookies, for example, like I'm just going to go with a simple cookie recipe, 1 cup of sugar and 1 cup of chocolate chips. Those are going to be pretty fantastic cookies, but 1 cup of this, 1 cup of this. Let's say that you have 20 cups of chocolate chips and 1 cup of sugar. Well, that 1 cup of sugar is going to be your limiting reactant. Now, this right here, this 102, does that change? Answer Y or N. Does this right here change our perfect ratio of our reactants to one another? It's different, but did it change our recipe? Is my question. No, it does not. It doesn't change our recipe. So think about the balanced reaction as our recipe, and we always have to go back to that recipe. So these numbers, these 102, that's like, here's a scenario. Here's what you have. Apply that to the rule. Okay. So now what I want to do, and we're going to build these out a little bit more. What I'm going to do here is we're going to look at another chemical reaction. So we have NaOH. And we're going to react that with H2SO4. What that will produce is, and this is not something that I'm expecting you guys to know the answer to because this is the information that I'm going to provide you. Na2SO4 plus H2O. So right here, this is a fantastic exam question. Or this is a fantastic stem for an exam question. I will give you this kind of foundation. I'll say, here's an unbalanced chemical reaction. And then my question is going to be something like, what is the coefficient before, mm, let's say, H2O, when the reaction is balanced? Okay. So essentially what I'm going to ask you to do is balance the chemical reaction and then identify the number there. Now, my first question for you guys is this balanced? Add it to the chat, Y or N. Nope, it's not balanced. Okay. Now, the next question is, well, what's unbalanced? And, here's those subscripts. In the event that you were looking at that poll question that we had earlier and you got mixed up about what a coefficient and a subscript is, these are the subscripts. You can't change those. So we're kind of stuck with those. Now, when it comes to a strategy for balancing a chemical reaction, what I always like to do is I like to try to balance oxygen, or I like to balance something that is unbalanced, but there's only like one of them. So, Emma, perfect. I see oxygen. And you know what? I see oxygen as a product here, 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 and here. And it's a number of different places. And my inclination is to say, you know what? I'm going to pump the brakes on oxygen just because it's in a bunch of different locations. The simpler response, in my mind, is to go after sodium because on my reactant side, I've got one sodium, and on my product side, I've got two sodium. So what I'm going to do is I'm going to put a 2 coefficient in front of that NaOH. Now, my question for you guys, after I put that 2 coefficient in front of NaOH, is the sodium balanced? Add a Y or an N to the chat. Got a Y. Perfect. Yeah, it's balanced. We're good there. Okay. Now, what does that mean? Okay, so what I want to do is I want to go ahead and list out my atoms. NaOH, NaOH. Okay, so on each side, I've got 2 sodium, 2 sodium. This 2 right here applies to that oxygen. So now I've got 2 oxygen there. I've already got 4 oxygen here. So I've got a grand total of 6 oxygens. Does everyone agree with that? Okay. So I've got 6 oxygens. Then on my product side, I've got 5 oxygens. Okay. Before I try to do anything, what I want to do is I want to go ahead and confirm that, account for all of my different atoms. So on my reactant side, how many hydrogens do I have? I've got that 2 that applies to hydrogen. And then I got this two. So I've got four hydrogen. How many sulfur? One. Now back to the product side. Well, I've got two hydrogen. And how many sulfur? Just one. Okay. So right now, I've got both hydrogen and oxygen, which are unbalanced or not balanced. And what I want to do, does anyone have any proposals on how to address this with a coefficient? Emily, 2H2O. Perfect. Whenever I throw that 2 there, does that change anything on my reactant side? It doesn't. Does it change my products? It does. It addresses both of the atoms that I'm interested in changing. For example, oxygen should now be, well, I still have these four, and now I have these two, so I'm up to six. Hydrogen, I'm up to four. Now, is my chemical reaction balanced? Perfect. Okay, so what I'm going to do is I'm going to erase lots of these arrows. I'm also going to erase the underlines where my coefficients could go. And what I want you guys to do in the chat is tell me what is the ratio of NaOH to Na2SO4. Add it to the chat. I'm seeing responses that are pretty much spot on. The only thing that I want to make sure that you recognize is on the left-hand side of my ratio is the sodium hydroxide. So that's going to get a 2 because that has that 2 coefficient. Then the sodium sulfate, Na2SO4, has a ratio of, or it's 2 to 1. Because all that I was interested in was these two things. Does everyone follow that 2 to 1 ratio? Okay. Now, let's say I wanted the ratio of, let's go with NaOH to H2O. Tell me that ratio. Just those two components, just those two compounds, NaOH to H2O. 1 to 1. You're absolutely right. It's 2 to 2, but 2 to 2 can reduce down to 1 to 1. So 1 to 1 is what I'm looking for there. Now, before we proceed, I've been saying 2 to 1 and 1 to 1. 2 what? And 1 what? What are the units for this ratio? I'll give you a hint. It starts with an M. Moles. Perfect. Great job. Awesome. Okay. So this is very valuable. And I'm going to erase all my other doodlings here. This is valuable because whenever you're confronted with different numbers, you can make an adjustment. So we have this kind of golden ratio. 2 moles of sodium hydroxide will react with 1 mole of H2SO4 to produce 1 mole of Na2SO4 and 2 moles of H2O. So that's our recipe effectively. Now, what that means is we can kind of respond to a situation or a hypothetical. So again, this is our recipe. We need 2 parts of sodium hydroxide to react with 1 part of H2SO4. Just to confirm, ratios are only seen between reactant and a product. We don't look at the ratio. Somebody just sent a private message to me, and it is a fantastic question. Ratios are only seen between a reactant and a product. We can look at ratios between reactants, and we can look at ratios between two different reactants to determine the outcome. So I want to go into that right now, actually. So here's our scenario. You have, let's say, 500 moles, and this is a good exam type of question, 500 moles of NaOH. My question for you is how many moles or H2SO4 moles are needed? Add that to the chat. 250. Because we have a 2-to-1 ratio. Okay. So this is sort of a like this would be a good STEM question where I present you with here's one piece of information. How many are needed? And the answer is 250. Okay. Now, another question would be here's a hypothetical. You have 500 moles of NaOH and 45 moles of H2SO4. Okay, so that's a scenario. And my question is anything, let me rephrase that, are any reactants left over? And answer that yes or no. Are any reactants left over when we have 500 moles of sodium hydroxide and 45 moles of H2SO4? We got a Y, a few. Okay. Now, my follow-up to that is which reactant is left over? Is it sodium hydroxide or is it the H2SO4? Perfect. It's NaOH because we have a 2-to-1 ratio. We need, for every one H2SO4, we need two NaOH. So again, go back to that idea of going through this reaction through rounds. Round one, we've got two NaOH and one H2SO4. Well, after round one, how many sodium hydroxide are left over? Add it to the chat. After round one, how many NaOH are left over? 498. How many H2SO4 are left over? Add that to the chat. 44. Perfect. Perfect. Okay. Can I get a response on a Y for I'm feeling good about this or an N, I'm struggling with it? Okay. Okay. Okay, cool. So this is basically three questions that would be good exam type of questions. I'd give you a number of one reactant, and I'd ask how much of another reactant is needed. I could also give you an unbalanced chemical reaction and ask you, balance this. Chances are, if I'm giving you questions, or sorry, whenever I give you these scenario type of questions, I'm going to give you the balanced chemical reaction. because I don't like to give a scenario question with an unbalanced equation where I basically am saying you have to balance this and then you have to do look at this scenario. Because if you run into problems with balancing, then you're going to run into problems downstream, and it's because you might have messed up the balancing. Well, we need to calculate like that 410 moles are left, or that's a great question. Um, that the question was, would we need to calculate the exact number of moles of sodium hydroxide that are left, or just know that it's excess? I'm not going to say that that's not a question that I would ask, but I would say that it's a kind of lower priority question. Um, because I want to make sure that you understand the concept and the process. And that's kind of like that would be like the sixth or seventh question that I would ask after this, if I do ask that. And I'm saying all that just because, you know, we only have like 40 questions on the exam. So that wouldn't be the highest priority. I hope that answers the question. Sorry for a very wordy response there. Um, but now that we have this, an understanding of how the reactants relate to one another, we can then go on to use our ratios of our reactants to our products. Okay, so here's another sort of question that you should expect to see. 500 moles NaOH and 250 moles Na2SO4. Na2SO4. Or, oopsies, H2SO4. How many moles Na2SO4 are made? Add your response to the chat or add your answer to the chat. 250. You're absolutely right. This is a good question where we can look at it and say, okay, well, both reactants, we've hit the perfect ratio of those two reactants. And then we can say, well, what is our relationship between either one of our reactants and our product? Well, it's a 1-to-1 ratio of H2SO4 and Na2SO4. Okay, so this would be 250. Now we've got 500 moles NaOH. So we got a lot of it. And 45 moles of H2SO4. Okay. Now, my question is, and this relates back to excess and limiting reagents. How many moles Na2SO4 are going to be produced? 45. Perfect. Next question, kind of tricky, but use the same fundamentals. We looked at what was our limiting reactant? H2SO4. What is our ratio of H2SO4 to Na2SO4? 1-to-1. Now, moles of H2O. How many moles of H2O are going to be produced? Before you, I'm not even mad, not even upset. Sarah responded before I could even ask my question. And you're absolutely right. It's 90. Because what we needed to do, great job, was we needed to look at our ratio of H2SO4 to H2O. It's a 1-to-2 ratio. As soon as we identify our limiting reactant, which is H2SO4, then we can say, all right, well, that 45 is effectively going to be kind of the determinant. It doesn't matter how much sodium hydroxide we have. I could have said you have 10 million moles of sodium hydroxide. It does not matter. We've got a 1 to 2 ratio between our limiting reactant, which I'm going to label this as LR, and our products. Our limiting reactant limits the amount of our products that can be generated. Okay. Can I get a Y or a thumbs up or a yeah, I've got it, I'm good? Something in the chat. Okay. 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 Good. Now, an important thing about all of this is we're putting it in terms of moles. So, what I want you to take away from that is you should always try to get things in the language of moles. If I told you you have 12 grams of NaOH, okay, I'm going to stop right there. Somebody asked me, I don't really understand where you got the 45 from. Can you explain that? Absolutely. The 45 was a number I just put out there. I just said, here's this hypothetical situation. You've got 500 moles of sodium hydroxide and 45 moles of H2SO4. Think about this as, this is a recipe. And just to kind of reiterate this point, I'll change the numbers. And these are numbers that I'm just making up. We've got 360 moles NaOH. And let's say 19 moles H2SO4. Okay, now I got to thank you very much. I'm happy that I'm doing this because I got a follow-up question. Okay, so if we had 360 moles of sodium hydroxide, hypothetical number here. This is not like, this was not on any other slide or anything like that where it's significant. 360 moles of sodium hydroxide, 19 moles of H2SO4. This is where we look at our stuff and we say, okay, well, we've got a ratio. We need to go back to our balanced chemical reaction. Our balanced reaction says 2 to 1. We need 2 moles of sodium hydroxide to react with 1 mole of H2SO4. So my first question then is how much NaOH do we, or how much H2SO4 do we need to perfectly react with all of that NaOH? Answer in the chat. I'm looking for the folks who sent me the message. How much H2SO4 do we need to perfectly react with 360 moles of NaOH? Well, it's a 2 to 1 ratio. So we need half. So we need 180 moles of H2SO4. Now, we take that number, we say, okay, that's what we need. Do we have that much? Answer in the chat, anyone and everyone. Do we have that much? We don't. So what that means is this is the amount of H2SO4 that's in our H2SO4 bank account. And this 180 is the amount of H2SO4 that we need. So are we going to be able to use up all that NaOH? Nope, we're not. So what that means is if we have less than we need, H2SO4 is our limiting reactant. So that's going to drive the ship. That's going to say how much of anything that we can make. Now, with that 19 determined, I could ask the question, or how many moles of Na2SO4 are going to be produced? Well, we use our limiting reactant, which is 19 moles of H2SO4. And somebody add to the chat, how many moles of Na2SO4 are we going to make? Close. We're going to use up all of our H2SO4 to make 19 moles of Na2SO4. I think the 18 was kind of tempting because it looked very similar to 180. But we're going to use up all of that H2SO4. We will use up all of our limiting reactant. We're going to spend it all. And we're going to get 19 moles of Na2SO4. Now, my follow-up question is, well, that's one of our reactants. Could anyone add to the chat what of, or sorry, that's one of our products. Anyone add to the chat what our other product is? Our other product is H2O. Now, add to the chat Y or N, yes for yes or no. Are we going to make H2O? Yeah, absolutely. We'll make H2O. Now my question is, how much H2O will we make? If we have a limiting reactant of H2SO4, 19 moles of it, we're going to use all of that. How many moles of H2O will we make? We got 38. We're going to make 38 moles of H2O. Why is that? Well, our H2SO4 is in a 1 to 2 ratio of H2SO4 to H2O. So we're going to make 38 moles. So somebody asked me where the 90 came from in the previous question. That's where effectively the 90 came from because we looked at the number of moles of our limiting reactant. So we had to identify our limiting reactant and then say, okay, what is our ratio of our limiting reactant to anything else? Everything about balancing a chemical reaction is about bringing it back to a ratio and establishing and identifying what a ratio is. What do we do with the excess? That is a fantastic question, Emily. That's an awesome question. So, with the excess sodium hydroxide, effectively, you know, let's envision this like taking place in the lab. We've got a big old glass beaker, and in that glass beaker, we've got all of that sodium hydroxide. And then we add some H2SO4. That reaction is going to take place in that beaker. And this is kind of a spoiler, but that sodium hydroxide is going to stay there. It's just going to stay there. And then you'll basically have to dispose of it. So, to answer your question of the excess, like what do we do with it? How do we deal with it? It stays there. I mean, from a practical standpoint, in terms of like a question like this on an exam, you don't really have anything to answer about that. But that's a fantastic question because it's just going to stay there. Cool. Can I get a Y if you're feeling good about this? Add a Y to the chat if you're feeling good about this. Okay, great. Okay, now, I think, yeah, there we go. What I want to do here is everything that we've been doing up until now has been using the language of moles. If I were to change it a little bit, and I mean, heck, we could go back to that same reaction. NaOH plus H2SO4 yields Na2SO4 plus H2O. And we have the coefficients of a 2 and a 2. So, will you have questions that relate to moles? Yes, you will. You absolutely will. Will you have questions that change things a little bit? And you're given something like you have 35 grams of NaOH reacted with, and let's say 22 moles H2SO4. My first question for you guys is how would you address this? What do you think your first course of action is? Add it to the chat. Perfect. Make the units the same. Do you think that you should go to make all the units grams or make all the units moles? Perfect. Make all the units moles. So in order to do that, well, I just remember from having done this sort of calculation before, 1 mole of NaOH has a mass of 40 grams. So with this number right here, do you have more than, less than, or exactly 1 mole of sodium hydroxide with 35 grams of it? Less than. Okay. So could anyone do the calculation to figure out the number of moles that we've got here? I trust that. 0.88 moles of NaOH. Okay. It's not a whole number. Is that a problem? Nope, not at all. So we're going to have 0.88 moles of sodium hydroxide and 22 moles of H2SO4. My first question, actually, this would be like, so the first question would be convert to the number of moles. Next question is, which is the limiting reactant? Yep, sodium hydroxide is the limiting reactant. Fantastic. That one's kind of easy to see because, well, the amount of H2SO4, and whenever, let me just clear the air. If ever I say, oh yeah, that's easy to see, that I'm not saying that like, oh, that's easy. I don't want you to interpret what I'm saying that way. Um, so 0.88 moles of sodium hydroxide and 22 moles of H2SO4. How many moles of H2SO4 will be used by the 0.88 moles of sodium hydroxide? This is kind of a tricky question, but let's look at our ratio. It's a 2-to-1 ratio. I always like to do this. NaOH to H2SO4. And then I'll say my number of moles, and this is a 2 NaOH to 1, 0.88 to X. Okay. Somebody asked me where I got the 40. This is just because stuck in my brain. Where would you get that number from? You'd get that from the periodic table. So you would take the mass of hydrogen, which is 1 gram per mole. Yes, you will get a periodic table, or if you don't get a periodic table, I will provide you with the molar mass. O is approximately 16 grams per mole, and Na is approximately 23 grams per mole. So I'm sorry about that. I should have. You will get a periodic table. If you don't get a periodic table, you'll be told there will be a statement in the question like this: 1 mole of sodium hydroxide is 40 grams. So that you don't, in that case, you wouldn't need the periodic table. Is everyone good there? Okay. So effectively, 0.88 moles of sodium hydroxide will react perfectly with 0.44 moles of H2SO4. There we go. So as soon as we determine by looking at our ratio at 2-to-1 And then we say, okay, how much are we given? 0.88 moles and 22. Well, this is our limiting reactant. My follow-up question for that is number of moles of Na2SO4 will be made. How many moles of Na2SO4 will be made? Go ahead and add that to the chat. 0.44. Okay. Can I get a Y in the chat if you follow that? Or say, hey, go back. Okay. Now, my follow-up question to that is number of moles of H2O made from this reaction. Add that answer to the chat. 0.88. Perfect. Okay. So you need to be able to go from mass to the number of moles. How would you do that? The periodic table will provide you the molar mass or the mass of 1 mole of a substance. And then you need to be able to identify the limiting reactant. Will you have questions like this where you identify the limiting reactant? Yep. Will you have questions like what you saw on the previous slide where you identify the limiting reactant? Yes, you will. Now, I'm going to give you guys a poll question. One last poll question. And then I'm going to say, have a wonderful afternoon. You guys did a great job. This is tough stuff. If you want to hang around and ask some questions, you are more than welcome to. I'd be glad to work through another practice problem with you. Um, Other than that, though, have a great day. Have a great afternoon. I will see you guys on Monday. So enjoy your weekend. Good luck if you guys have any tests the end of this week. And then to answer this question, the reactants on a chemical reaction are found to the left or the right? Well, right now I've got it's a pretty close battle, but it is going to be to the left. The reactants are found to the left. The products are found to the right. Okay, everyone. Well, I'm going to go ahead and stop my recording. And again, if you got questions, hang around.